In this video, we're going to talk about the credibility of science. So what makes science credible? And then we're going to talk about bias, results, how they can be repeated and what that looks like. And then we're going to talk about percent error in regards to accuracy and precision. And then we will do some practice with that. So let's jump in to what makes science credible. And you will remember that this question, what makes science credible, this is one of our guiding questions for the unit. So there's a few different ideas listed here, but this is not an exhaustive list. There are a lot of other things too, but this is a good starting point. So what makes science credible? So number one is the elimination of bias. And down here, we will talk exactly what it is in just a second. Number two, following standardized lab procedures. So standardized lab procedures, we've been talking about those. So experiments have a control group. They have constants. They have variables. They're only testing one variable at a time. So we've been talking a lot about those. And along with those standardized lab procedures, we're also looking at measurements. So do we use significant figures? Are we measuring correctly? Number three, results can be repeated. If results can be repeated, that helps validate scientific findings. And then number four is a low percent error. So what makes science credible? Having a low percent error. And we will talk about these things more in just a moment. So let's start with bias. In science, we want to be objective, not subjective, which means that we don't want to include our opinion in what we're doing. So bias then is a particular preference or point of view that is subjective rather than objective. So bias compared to science, opposites, right? We can see bias is subjective rather than objective, and that's not what we want to be in science. We do not want to have our opinion. So you can kind of think of bias as being synonymous with opinion. Now, everybody has bias. Everyone has it, whether you know it or not, we all have some sort of bias. And so scientists work very hard to take their bias out of what they're doing. And there are certain ways that that can be done. And that also has to do with standardizing our lab procedures. So in an example here, we're going to find a way that they eliminated bias. So it says a company wanted to begin manufacturing and promoting a floor cleaner that it claimed would clean floors better than the previous products. The company sent its products to two independent research groups, which determined the floor cleaner did clean floors better than the previous products. So we want to know, how did they come to a bias-free conclusion? So pause the video for a second and think about this, and then we'll go over it. Okay, so the key phrase here is that they sent out their product to two independent research groups. So if they are going to independent research groups, that means they're not doing the research themselves. If you are getting a floor cleaner from a company and they proclaim from their research that theirs is the best, it's like, can I really trust that? Whereas they sent their product to an independent, so another research company, and that verified it. So that is a great way. Now, this is only one way that bias can be eliminated. So this independent research, that is one way. There are all sorts of controls that happen in an experiment. Now, controls not meaning a control group, control meaning things that you control in the experiment, such as making sure we have a blind study. You might have heard of that before, or maybe a double blind study, so people don't know what they're testing. That can also help eliminate bias, because if you know what you're testing, you might lean one way or the other. Now let's talk about these results that can be repeated. So when results can be repeated, so if you are a scientist, you do research, and then I'm a scientist and I follow your research and I try it myself and I come up with the same exact results, that really helps validate the scientific finding. So that helps make it true, because if we can both do the experiment and get the same results, that's a really good sign. So let's take this validating of scientific finding and let's really expand upon that. So now let's talk about scientific theories and laws. So a scientific theory is different than saying in normal speak, oh, I have a theory about that. because a scientific theory is something that has been validated multiple times from scientific evidence from multiple resources. So when we say a scientific theory, we are talking about an explanation of why something happens based upon scientific evidence. And this theory, the results of it have been repeated. So it's not just some sort of theory someone had. No. This goes through a very rigorous process to make sure the scientific finding is valid. But when we hear gravity's a theory, we don't think of it just as, oh, gravity's a theory, and then we fly off the planet, right? We are grounded to this planet, so when we hear a theory, we really want to think about how valid the scientific finding is. Now let's talk about a scientific law. A scientific law is a prediction of what will happen based upon scientific evidence. So our prediction, let's stick with gravity here. So if you drop a ball, what will happen? Well, the ball's gonna fall to the earth, right? So this is a scientific law that tells us what will happen. And once again, this has been validated multiple times. So results can be repeated, and science helps science become credible from that. Up next, we are going to talk about percent error. So a low percent error helps make science credible. So let's talk about what percent error is and where that comes from and the different parts of it. So percent error. Whenever we are looking at the authenticity of data, there are two main methods used, and they are accuracy and precision. And there is actually a difference between accuracy and precision. A lot of times these two words get used interchangeably, and they're not the same. So percent error is broken down into really looking at accuracy, but it's important to talk about precision to know what that is as well. So accuracy is how close a value is to the actual or accepted value. Precision is how close values are to one another. Let's move on and look at these targets. So looking at these targets, whenever you are aiming for a target, you're always aiming for the center, right? We want to get bullseye. So if you hit the bullseye on a target, you are being accurate. Or if you get close to the bullseye, you're being accurate. If you're precise, all of your shots on the target are going to be close together. So let's start labeling some of these targets. So if we get very close to the bullseye, we are being accurate. So this target here is accurate, but our values are not close together, so we are not precise. So we're accurate because these are very close to the center, but they're not close to each other, so they're not precise. On the flip side of that, let's move to this target here. These values are not close to the center. They are very far away from the bullseye. So because of that, it is not accurate. However, the values are close together. So all of those dots right there, very close together, which means they are precise. So now let's see our other two targets. This target over here, it's close to the bullseye, which tells us it is accurate. And all of those values are clumped very close together, so it's also precise. So this target is both accurate and precise. Let's look at our last target now. For this one, the values are not close to the center, so it is not accurate, and our values are not close together. So it's not on the bullseye, and they're not close together. So this one is not precise. So that's looking at targets, but we're gonna shift gears now and talk about data because that's a little different. So the targets are really helpful conceptually, but now let's see what's going on with data. So we have some data here, and students are getting the melting point of sucrose. Sucrose is just sugar, so think table sugar, that's sucrose. And they're trying to melt it. So you can imagine putting sugar in a tube and then they're trying to melt it and figure out what the temperature is. Now, it is known that the melting point of sucrose is 185 degrees Celsius. So all of these students are gonna go through this trial and see what they come up with for their melting point. So let's find the most accurate and the most precise. So if we have the most accurate student, they are going to be closest to the actual or accepted value. So pause the video, try to figure out which student is closest to this accepted value. All right, for this one, student A is the most accurate, and it's because their average here is closest to 185. 184.7 is closer to 185 than the other two students. So how do you know? Their average is closer to the accepted value. Now we want to look at precise. So when we look at precise, we're going to be looking at the trials and seeing how close their values are to one another. So pause the video and see if you can figure out which student is the most precise. Okay, student C is the most precise student. And that's because their three trials are the closest together. So if we look at the range of the data for student C, they have the smallest range of data. Now that you know what accuracy and precision are, we can talk about percent error, because percent error is really just a measure of accuracy. So it's a measure of how close the accepted and experimental values are. So it is a measure of accuracy. So when we are looking at student A up here and seeing that they are the most accurate, we can quantify that. We can quantify their accuracy, and that's what percent error really is. So if you are doing an experiment, you really want to have low percent error, because low percent error is really good. That means you did not make a lot of mistakes. If you have a high percent error, that's really not good. That's bad. If you had a high percent error, that means you made a lot of error. So we are looking for the lower number, the more accurate it is. Here is the equation for percent error. So percent error is equal to, and this is the absolute value of the experimental minus accepted divided by accepted times 100. So if you have not seen absolute value before, all that means is that your answer becomes positive. Some calculators have absolute value bars on them and some don't, so I will be showing you how to figure it out without them. So we're going to talk through student A's example together, and then we'll pause the video and let you work through student B and student C's. So let's start with student A. So we need a few numbers from student A. So looking at this equation, we need to figure out what is the experimental and what is the accepted. So we need to figure that out. So let's go back up to student A. Student A did the experiment 3 times and they got an average. So we're going to use their average, which is 184.7, because they did the experiment and this is the value they got from the experiment. So 184.7. Now we need to know the accepted value. So the accepted value, it says on the chart, is 185. The next thing we're going to do is we're going to pop these numbers into the equation. So this experimental will go here, and accepted will go in 2 different places. And let's put this into our calculator. So we're not going to use absolute value in this calculator. If your calculator has absolute value, awesome, go for it. We're going to talk about how to solve this without it. So we have parentheses 184.7 minus 185, close parentheses, divided by 185. So this is our first step. So when we put that in our calculator, we get a long number. So now let's incorporate absolute value. So we notice the number came out negative from the calculator. In order to use absolute value, we just make the number positive. So we're going to forget that negative sign and just make it positive, because absolute value just means we have a positive answer. So let's use sig figs here. Our answer should have 3 sig figs in it so far. So we have 0.00162. And now we're going to multiply that by 100. And for our final answer for student A, we get 0.162%. So to recap what we did to solve that, we figured out what the experimental and accepted values were, and then we set up our equation. So we had the experimental minus accepted divided by accepted, just like this, times 100. We put that into the calculator. We got our sig figs, made it positive because of absolute value, and then multiplied it by 100 for our final answer. So go ahead and pause here and try student B and student C. and then we'll go over the answers in just a moment. Okay, let's talk through student B and student C's percent errors. Let's start with student B. So student B had an experimental value of 186.8. So we found that by looking at the average, so 186.8, and the accepted value stayed the same, it's 185. So let's fill in our percent error. So percent error says we take the experimental 186.8 minus the accepted 185 divided by the accepted times 100. So that equation came right from here. So the next thing we need to do is we need to put this in our calculator. And this gives us 0.009729 blah, 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 blah. So sig fig wise, we're only going to use 3 sig figs here. So we'll have 0.00973. And then we need to multiply that by 100. And our final answer is 0.973%. Now, you'll notice it was already a positive answer here, so we didn't have to do anything with absolute value. Okay, let's look at student C. Student C, experimental, we got that from the chart, and it was 186.8. Well, hold on, that was the wrong value. Sorry, 181.6. 181.6, sorry about this. All right, 181.6 minus 185 divided by 185, and then we'll multiply that by 100. So if we put it in the calculator, now we see a negative number there, so we're gonna have to make that positive because of those absolute value bars. And we have 3 sig figs in our answer, so we have 0.018, and then that 37 rounds to a 4 here, times 100. For our final answer, we have 1.84%. So those are our percent errors for student C, B, and C. So now our last question on our note says, does this percent error match the previous findings about which student was most accurate? Why or why not? Okay, so this one does match who is most accurate. So up here, we figured out that student A was the most accurate. Well, that makes sense with our percent errors, right? We said low percent error is good. So the lower the percent error, the more accurate they are. So lowest percent error goes to student A. So student A has the lowest percent error. That wraps it up for credibility of science notes.